Chapter 17 is about different particular applications of aqueous equilibria. And it opens up with a very important concept called buffers. And there are actually different kinds of buffers, but what we usually mean, and what we definitely mean in this case, are pH buffers. And pH buffers are solutions which will resist changes in pH. You can dump strong acid into a buffer solution and the pH won't change very much. And you can dump strong base into a buffer solution and the pH won't change very much. And it's almost magical until you learn the secrets of how buffers work. And today I will teach those secrets to you. So buffers are present, they're ubiquitous really, in nature all around us. Our own blood is a buffer, ocean water is a pH buffer. Basically every aqueous solution that we find in nature is going to be a buffer. And so it's going to be really important for us to understand how they work. So first of all, let's consider the reaction of nitrous acid with water. So if I have HNO2 plus H2O, nitrous acid is a weak acid, so we'll be in equilibrium with NO2 minus plus H3O plus. If we think about it, if we add nitrous acid to water, then it will begin at a pH of 7, it will begin neutral, and then as this reaction proceeds to the right, then it's going to change the pH by producing some H3O plus. Now what if I add something like sodium nitrite to that solution? Well, now I've added a product, and that's going to drive the equilibrium left, and it's going to, in the process, consume some of that hydronium ion and bring the system closer to a pH of 7. That's all just based on the Chatelier's principle. This is an equilibrium, and NaNO3, when it's in solution, will break apart into Na+, which is pretty irrelevant to us here, and to, oops, that should have been NO2 all along. That's sodium nitrite. And NO2 minus, which is our product here. I apologize for that. Sodium nitrate would actually have no impact. But sodium nitrite, the Chatelier's principle says if we've added this product, it'll drive it to the left. And the impact on pH will be that the pH is pushed back closer to neutral. And so any equilibrium pH, solubility, and any other equilibrium reaction that we investigate will be influenced by adding some soluble ionic compound that contains an ion which participates in that reaction. So this is called the common ion effect. Because this reaction and this compound share the nitrite ion in common. It's in both of them. Okay, so that is the common ion effect. And that's just a little bit of an intro to what happens with buffer solutions. Because when you add some nitrite to your nitrous acid solution, what you've actually created is a buffer. So a buffer solution, we'll end up rewriting this equation later, but a buffer solution is a solution which contains both the acid and base in a conjugate pair. Both the acid and the base of a conjugate pair. And so why is it that having both the acid and the base in the conjugate pair is going to create a buffer solution? Well, first of all, based on the common ion effect, we can predict that the pH of a buffer solution isn't going to be as extreme as the pH of just a pure weak acid or a pure weak base, right? Having both of them present kind of pushes the solution at least somewhat closer toward neutrality. But the real magic comes in when you consider what happens if I now take this buffer solution and I add strong acid to it. And I need to back up real quick because I've made a critical omission here. These must be a weak acid-base pair. A weak acid and weak base conjugate pair. Strangely enough, the strong acids and strong bases, they're not going to make buffer solutions at all. It has to be a weak acid or a weak base conjugate pair. So let's consider buffer plus some strong acid like HCl. If I put HCl into water, then it will just dissociate, it'll create H3O plus ions, and it will tank the pH down to low acidic numbers. But if I put HCl into a buffer solution, it's actually going to react, and I'll call these just A and B. Okay. Those are the acid and base conjugate pair. I could have called them HA and A minus, or I could have called them B and HB plus. I've kind of used that notation in the past, but I think it's easiest to just call them A and B, the acid and base part of a conjugate pair. So if I add hydrochloric acid to a buffer solution, then this is the chemical reaction that will occur. HCl plus the base, and this is not an equilibrium reaction, this one will go to completion, will form the acid, right? That H will be donated to the conjugate base and convert it into its conjugate acid, which is the acid component of our buffer, plus Cl minus. And what we see here is that the hydrochloric acid now, instead of generating H3O plus as its product, it has generated only a weak acid plus an inert chloride ion. And not only is this acid weak, but this weak acid is being influenced by the common ion effect. So we have A plus H2O in equilibrium with B plus H3O plus. Here we're revisiting that equation like I said we would. And not only have we taken the strong acid of HCl and converted it into a weak acid, but even that weak acid is going to have its equilibrium pushed closer toward neutrality by the presence of its conjugate base through the common ion effect. And it really undercuts the effect of the hydrochloric acid. We'll do some math in the next section to sort of prove how dramatic this effect can be. But hopefully you can at least understand the idea behind it. If I add hydrochloric acid, it will react with the conjugate base, but that conjugate base will be converted into its weak acid, and as long as there's at least some conjugate base left over, then that weak acid is influenced by the common ion effect, and the pH does not change very much. Okay, what if we go the other way? What if we take a buffer plus a strong base, something like NaOH? What is the NaOH going to do? Well, the NaOH in water just produces hydroxide ions, and the pH will skyrocket up to basic values. But if I add NaOH to my buffer solution, it will react with the conjugate acid. And that will produce that will produce the base plus water, because the acid will give an H plus, and we'll be left over with Na plus. Okay, and we've got the same thing going on. This strong base is now converted to a weak base, and that weak base, furthermore, is having its basicity suppressed through the common ion effect by having its conjugate acid present in solution as well. And so instead of having the pH go up and the hydroxide concentration go up, instead that NaOH is absorbed and the pH isn't affected very much. So we can see this in figure 17.1. If these bars represent the quantity of the conjugate acid and the conjugate base pair, here they've used HA and A minus. Perhaps that's what I should have done. But these are the conjugate acid-base pair. And these bars represent the amount that we have in solution, so they're equal to each other. If I add some acid, that will react with the base, and so the amount of base will go down. And it will produce some acid, so the amount of acid will go up. But the pH of this solution, where the conjugate acid-base pairs are equal, versus this solution, where the conjugate acid-base pair amounts are just slightly askew, those pHs we'll find are very similar to each other. If we add base, we have the opposite effect. The base will react with the acid and drop the amount of the conjugate acid. It will produce a little bit more of the conjugate base. And so this ratio skews now toward the base. And the pH will change a little bit. But again, we'll see that the pH does not change very much between these two. And we'll investigate this mathematically in the next section, as well as really rigorously discussing the concept of buffer capacity. But as long as I have this figure up, I just want to point out that that a buffer cannot work like to an infinite degree. If I'm adding acid and it's reacting with the conjugate base, at some point the amount of conjugate base gets less and less and less and less and less until there's none left. If I add as much strong acid to the buffer solution as I need to completely consume the conjugate base, then hopefully you can see it. At that point, our buffer is not going to be able to withstand changes in pH anymore. There's no sink left to react with any additional strong acid once the conjugate weak base is consumed. And we can say the same thing about adding base. Once I've consumed all of my conjugate acid, then any additional base I add is going to just act like a regular base and increase the OH minus concentration. So that's just a little intro to buffer capacity. Again, we'll show you how to deal with this mathematically in the next section.